Okay, so I will start now. Good morning. We are going to introduce you how to do big data and machine learning with fiware. It's really easy if you know what you want to do. This is the main problem of this kind of things. A lot of people talk about big data and machine learning, but the key is to know what you really want to know and what you really want to have with your analysis. The advantages of fiware is that we have already a very easy way to connect to the data that is in the context broker. As you know, this is the key point for any architecture based on fiware. And we have developed all the connectors where you will see that with very little code, you are able to use this kind of environments. Right now, big data and machine learning are one of the most active fields in several aspects of academic and also in industry, and even normal people have heard it and is knowing which already been done inside it. This is key if we really want to have smart environments. The smart part will come from the machine learning and the different analysis that we can do with big data. So we must take into account that to really have something smart, what is called wisdom, comes from doing a lot of things with the things that we have. Most of the fiware architectures are based on different IoT sensors and other kind of things that go to the context broker. This means that we will be here, we are with the data. Once we start processing it, we will get more information, and later using machine learning and other techniques, we are able to get knowledge or finally wisdom, that is how to apply this knowledge. Here is where the smart part comes. This is the data that we get, and we move from getting something that is called smart, that is what people is expecting to get from the data. Most of the people don't know exactly what to do with this data, but we need to have different tools that are able to process and get the things that we finally need. There is a lot of people that confuse machine learning with big data. These are first, big data is nothing new. It's something that has been done since the 16th. It's just that what have changed is the big part. Before, there were a lot of techniques for analytics, data analytics, and then we move to something that is bigger. Right now, we have environments where we are able to handle a lot of data. We must take into account that big data is something that not all people need. Let's say that big data is when you need more than one computer to process your data. If your data, due to the special characteristic for the volume, for the velocity, the variety, or the veracity of the data, probably you need a cluster that is needed in the cloud to process it. If not, you don't have a big data problem, and you can use several tools. Are more simpler, and in big data, we have the overhead to have this fully scalable. This means that we need just to be able to make several computers collaborate to solve the problem. This means that we have a little overhead for this collaboration. So once we have the big data problem, then we can do other things. We can do data science, artificial intelligence, etc. Data science is the common way now of handling data, where you make some suppositions on it and then you change and analyze it. And later we can do other things with the data in order, for example, to predict what will be the data that will come in the future. We will see later this in the example. Here in artificial intelligence, there is a lot of techniques. Some of them are machine learning, but not all of them. So when we talk about artificial intelligence and machine learning as synonyms is not true, are different things. And inside machine learning, there is a special type that is quite on fashion now, that is deep learning. It's just a special type of machine learning that due to the fact that now we have more faster computers, we are able to handle this kind of things. Also, again, machine learning is not new. It's just that we have now more powerful computers to handle it. But the base of it was in the 70s and in the 80s. So once we have the technology for big data, we will try to do something that we will use a machine learning algorithm. And this machine learning algorithm, we will try to match our data. This means that we have different types of machine learning algorithms. We must take into account that for each kind of problems, that means some statistic distribution for the data, there should be different machine learning algorithms that suits more the data. So there is not a single algorithm for all the fields. For each of them, we should check this. Each algorithm, when we have trained it, we will get some results. That means how accurate it is. In some cases, we should run different algorithms and just choose which one is the best for this. This is usually a task for data engineering, that they know more or less which are the, depending on the data, which are the right machine learning algorithms, and these ones will be the one chosen. Well, the process will be that we need to train the algorithm. To train the algorithm, we need a training data set. Sometimes there are algorithms that are able to handle this from the normal data, but the self-learning algorithm, but in general, we will need a training data set. Once we have trained the machine learning algorithms, we will get a model, and later we will use this model for different things, usually for making predictions or to recognize things, depends on, again, on the problem. This is a very wide way of using. We should have also different things for this kind of problems. We must take into account also that the choose of the right data set is quite important. So also part of this engineering process is to choose the right data to train everything. Some data sets, for example, could be anonymized, and to anonymize, we may have introduced or destroy some statistic property, and some algorithms may not work with this kind of things. There are a lot of tools, Spark, Flink, TensorFlow, Keras, a lot of them, that we must choose which one will be used for machine learning algorithms. We must take into account that not all machine learning algorithms could be run with real big data problems, especially due to the fact that not all algorithms could be parallelized. But well, this is a problem that we will have. In our case, as I mentioned, we will get the data, we will get it, storage, and later processes. This will be the architecture that we will be sure later in the examples that we have. So we have a lot of data injection. This means that a lot of places that are producing the data. This will come via different interfaces. All of this will be into the context broker, where will be put in NGSI version 1, 2, or NGSI LD. And then we need to make a way to connect to different databases and also different systems where we can put it. So you can use different tools that depends on the problem. We can use STH Comet, Quantum Leap, or Draco. That will mean that we will get the data in different systems. This means that we will be able to connect here databases, or here in our case via Draco, we can connect directly Spark, Scala, and Apache Flink. These are very two well-known environments and are the most used in the industry. Spark Scala is the most generic for big data and machine learning in most cases, and is able to use other things inside for deep learning and other kind of algorithms. And Flink is more intended for stream processing. Even Spark also has some stream processing. So depending the problem and the algorithm we want to use, we should choose one of these. Although we can also connect other things via the different databases that we have here. In our case, the most general one, as I tell you, the most widely used by the industry is Spark Scala. It's really an amazing algorithm that allows to distribute data in any cluster in a very transparent way. This means that we can put a cluster of computers, and it will self-balance and will do all the magic to do the parallelization for it. Spark Scala have different libraries that could be used for querying via something similar to SQL, the streaming for trade data in a stream in Windows of data, the machine learning part where we can choose several algorithms. Remember that we choose these algorithms are the ones that are able to be parallelized, and something for trading a graph of data that could be inside it. We have an alternative to Spark streaming that will be the one that is called Spark Apache Flink. I don't enter in the details, but here I have a special magic that is called the distribution of it. And what it will do is the algorithm we write in a very high level way, usually in Scala and now in some cases in Python, but we recommend you Scala is the most powerful language for this kind of things. And other problems of this kind of things will be automatic parallelized in a graph that will have some tools, and without our intervention, just telling how many machines it will be able to run, it will parallelize the problem and be able to handle this. This is key if we have really big data problems, because we need several computers to finish our analysis or our machine learning part. As I tell you, for some streaming cases and also some machine learning problems, we can use Apache Flink. Apache Flink is not so general, but is more intended for real-time events. The size of the time window is different in Spark Scala streaming and Apache Flink. And if we have a very fine-grained one, we should go for Apache Flink. We have also the connector ready, so it will be very easy. Here, we will write also, could be used Java, Python, or also Scala, where we can do some analysis on the data we have, and again, getting some result for it. So we must take that into account that the cycle will be not that we put the data directly to the machine learning things. We must go first to build our model. This means that we will get first some data. As I tell you, we must choose a subset of it that is quite representative for the data we are having. This is the one that we will use to train our model. It will be, let's say that we have different phases and different parts in our tools. So once we get the data, well, in Draco or in a database, we choose a part of it. We build our model. They will take, in some case, some time, depending the algorithms and the resources that we have. In some cases, we may need to use GPUs or farms of GPUs that as they are available on Amazon or on Google clouds. Once we have it, we will have a model. With the model, we are able to put the model in production, something that will execute the model, And when it gets, again, some data, we will get the result that we want to predict or whatever we want to do with our model. This means that can do several iterations, and if we see that this model should be changed or whatever, we can choose another kind of data, and then we can build another models. In some cases, the model should be rebuilt depending on the data. If the data changes a lot, something that is, for example, changing all day, like some money values, or depending on the applications, we need sometimes to rebuild the model. In another problem, once the model is built, we can use it without changing. It depends on the problem and if this data and the things we are ingesting are changing a lot or not. Once we have this done, we can get different things in the results. Here, as I tell you, it's very important to choose the right machine learning algorithm we are using. In some cases, we can use several in parallel, or well, depend on the problem. Here is what more of the science is. As you see, this process is quite similar to the one that you can do as data engineer with the notebooks or whatever, but just will be done with the fiware data in a very easy way. For example, one of the most simple algorithms to understand are the decision trees. The decision trees are very well-known machine learning algorithms, and we just try to make some decisions. The decisions depends on the data, and we try to adapt our problem and build this kind of tree. So it's like a flowchart. We take decisions on the data, and this means that depending on this, we get several decisions on this. It's very simple, and sometimes it's not too accurate because this is sometimes not the best solution. So some cases we make not just one tree, but a forest. And as one tree that usually we don't get a lot of good results, we use a tree, a set of trees that will be our forest. Random forest is a generalization for this. We have with the decision tree that is very simple, can get better results. And in these cases, we get a set of trees, and depending on how they run, sometimes we get a lot of better results to get the right decision for something that is provided by our data. In the previous case, you understand the tree. In most cases here, the trees are not very easy to understand, are more intended, since are intended to be understood by a machine, not by a person. So, for example, in this case, we will get a lot of trees that are able to do something. We get the input. Remember, first we get the training data. With the training data, we generate the different trees. And this is what we deploy later with our data. Once we have it, we will have different predictions. And for example, we can make an average of all predictions. This is what we will get as a random forest prediction. For example, this is one of the most easy to understand machine learning algorithms, and usually you get better good results. In our experience, this is the one you can use or try to use first, and see later if other machine learning algorithms that could be more complex are better than this. Now there is a lot of fashion on, as I tell you, in deep learning that uses the artificial neurons of different levels, but it sometimes requires a lot of computation, and you sometimes don't get better results than random forest. But well, this depends again on your problem and on your data. So this will be the architecture of the solution that we will introduce now, that will be introduced by Andrés.
Okay, in the previous slide, Joaquín mentioned that we have some generic enablers that we need to include in this type of environments in order to provide some special features for performing machine learning and big data. One of these generic enablers are Draco. Draco is a generic enabler in charge of takes care of the data ingestion and persistence in an easy way. We use Draco for connecting this generic enabler directly to the context broker and using this component for storing all the information that the context broker receiving anytime. This generic enabler is built on top of Apache Nifi. That is a very powerful engine that allows to perform some operations based on the concept of flow-based programming. That means that we, with this processor, with this component, we can define a series of pipelines for performing many operations over the data as it comes at the time as it comes. So we can talk that we can perform that operations in soft real time. The basic architecture of this generic enabler is, as you can see in this slide. This architecture based its core components in processors and controllers. The processors are all the pieces of software that allow us to perform some operations of the data, and the controllers are the pieces of software that allow us to connect to different systems. So with the combination of these two pieces, we can perform some from very easy operations to very complex operations in big data environments. We have also the flow file, the content, and the provenance repository for managing different type of operations. In this case, the flow file stores in memory all the data and all the objects for performing operations. And the provenance repository gives us the possibility to map all the operations that we can do with the data or that we did with the data in any time. Finally, Nifi provides us a web server that allows to the user to define all the operations that he wants to perform over the data through a graphical interface. So with this application, we only have to configure some processors in an easy way. How does Draco is integrated in fiware? In this slide, we represent in a very good way how we can introduce Draco in the fiware ecosystem. As you can see in the left side of the slide, we have the data sources that can be many IoT devices or sensors or many other things that are directly connected to the context broker. And also in the middle part, we have the Draco that is connected to the context broker. How we can connect Draco with the context broker? This is thanks to the subscriptions capabilities that the context broker has. So we make a subscription from Draco to the context broker, and then we receive notifications for every change that we have in the context broker. It is important to remark that the context broker only stores the last value of the data that he receives. So that is the reason that we need to connect Draco, because every time that we receive a change, we can use Draco for storing these values in different databases that we need to store. In this slide, you can see that we can work with MySQL, Mongo, Postgres, but we have also more storage systems that have been integrated in Draco. This is a little review about the features that we have with Draco. Draco, as I told you before, is based on Apache Nifi. So in this case, we have all the features that this software provides us. We also have native NGSI v2 support for ingestion and serializations, and the integration with the Orion context broker. So we don't need to perform some additional operations or many other special configurations in order to integrate Draco with the context broker. This is very easy to manage and is in the same way that all other generic enablers connected to the context broker through subscriptions and notifications. In this case, this is a list of the several backends or several databases that we provide with this software that we have right now in Draco. So we can use Draco for stored information, store the context information in MySQL, Mongo, Postgres, HDFS, Cassandra, CartoDB, and also in DynamoDB. Another things that we provide with this generic enabler is a series of templates. So the user only need to drag and drop some templates and have all the scenario up and ready to use. And also the user can modify all of these pieces of software depending of their necessities. Finally, Nifi also provide a REST API, so we can automatize everything in the part of configuration and the running part in this generic enabler. In this slide, we can see a basic example of how Draco works or how Draco looks like. So in this case, the example show you that we receive a notification. This notification is catched by Draco and then will be persisted in MySQL. The graphical interface is shown in the right part of this slide. As you can see, we have three processors in this picture. So the first processor is in charge to receive the notifications coming from the context broker in this case, or any other data source. We receive this notification and then pass this notification to the next processor that is NGSI to MySQL that will perform some operations in order to create the database, create the tables, and also store the data directly to MySQL. And finally, a third, but is an optional processor that is in charge of show the login information about the whole process that we perform in Draco. So as you can see, it's very easy to configure and to use. So we also provide some tutorials in order to provide a deeper examples for using this software. So right now I am giving the word to Sonsoles. So thank you.
So we have seen how to save context data in a database thanks to the Draco generic enabler. But sometimes it is useful to analyze data in real time as soon as they are available. In the case of fiware, this happens through the context broker. That's when a piece of data arrives at the context broker, we know it's available for us to use. So instead of static data, the one that we save with Draco, we have streaming data that we want to analyze. So the generic enabler in the fiware ecosystem that allows us to perform real-time analysis on streaming data is Cosmos. Normally, big data engines integrate within their APIs features to easily read data from databases, from files, or even in the case of streaming data from sockets or other continuous sources of information such as Apache Kafka, for instance. However, we need a way to receive data coming from the context broker in the fiware ecosystem, and these data are in the NGSI format. So we need a way to receive these data in the NGSI format directly within our data analytics jobs. So in order to do this, we can use the connectors provided within Cosmos to receive the data coming from the context broker, process this data any way we want, and then save the result in a database, in the HDFS, or send it to maybe a web service, or even write it back in Orion so other fiware components are notified of this result and can make use of it. So right now, the Cosmos generic enabler provides a connector to connect with Flink, which Joaquín explained in the beginning. It is a big data engine to process real-time data. And as we can see in the diagram, the connector is included as a part of our processing job. And it has two parts: the Orion source that allows us to receive notifications through HTTP directly within our job, and then write the result back in the context broker using the Orion sync. We have the exact same thing for Spark, precisely for Spark streaming. Using the Orion receiver, we receive notifications within our Spark job, and then whenever we process the result, we can use, if we want, the Orion sync to write the result in the context broker. Both connectors are available for you to use. They are documented. They have a set of examples, so it's easier to get started, and also a step-by-step tutorial. And they are both compatible with NGSI version 2 and NGSI linked data. Okay, so now that we've seen the two main pieces besides the context broker that we need to perform big data analysis using fiware, we're going to present a use case that maybe will allow you to understand better how to get started with this. So in order to depict how it's done, we have chosen this use case, which is called predicting supermarket purchases, and it's based on a real scenario that I'm sure most of you have experienced before, which is just walking inside a supermarket and seeing a really, really long line and just going back out because it's impossible to buy something. So what if supermarket managers could predict how many purchases there's going to be at a certain time, so they could dimension the number of cashiers that should be hired for that time? So that's exactly what we're going to do now. We're going to provide a way for supermarket managers to predict the number of purchases so they can better manage the number of employees at all times. All the code that we're going to show and use now is available on GitHub for you to see or download. The only dependency that you need to run it is Docker and Docker Compose. Since everything is inside containers, you don't need to install anything else. Okay, so the first thing that we need to predict the future is data from the past. The best predictor of the number of purchases there's going to be at a certain day is knowing the number of purchases there was on a similar day the previous week. So we actually managed to get a real data set from a supermarket, and this is what it looks like. As we can see, it has several columns that represent the different date components: the year, the month, the day, and the time of the day. Specifically, each row represents a 1 hour interval. So the first row would be from 12 a.m. to 1 a.m., the second row from 1 a.m. to 2 a.m., and so on. And the weekday represents on which day of the week that day fell into that specific year. For instance, I think weekday 3 was Thursday. And that is of relevance since people don't shop as much on the weekends or as on the weekdays or the other way around. We don't know. That's why we're trying to see. So we think it has some impact on the results. So that's why we included it in the data set. Well, and obviously the last column is the number of items, the number of purchases, the number of clients that were in the store at that time and bought something. And that's obviously data that we gathered from the past. And what we're trying to do here is to predict the number of purchases for a future date that we don't know yet. So the first thing that we need to do, as Joaquín mentioned earlier in the machine learning lifecycle, is to use this data to train a model using an algorithm, and so we can later use this model to perform predictions. In this case, for these specific data, we have chosen the random forest regression algorithm. As we saw earlier, the random forest algorithms work pretty well because they use several different decision trees in order to get a more accurate result. And in this case, we actually use the regression part, the regression variation of this algorithm, because what we are trying to predict is a number. It's not a classification problem, for instance, in which maybe we could get a yes or no output, or I don't know, in a medical recognition, medical imaging recognition, we could identify whether there's a tumor in an image or not. But in this case, what we're trying to guess is just the number of predictions, so that's why it's a regression problem. So if we take a look at the code, I don't know if I will be able to. No. One second. Can you see the other tab? No, right? I need to change what I'm sharing. One second. Can you see it now?
Yes.
Okay, thank you. Okay, so this is the code. Well, I don't know if you. It's in the bottom right corner of the slide. In this code, we will see it very quickly. Wait, this wrong code. This one. Okay, in this code, what we want to do is to import the data set that in which we have the data from the past. We have to specify the shape of this data set, the columns that we have, and we have to specify which of the columns are going to be the features of the model, right? The things that we will know in the future, like when we want to predict, we need to specify the date, and what we don't know is the number of purchases. So the part of the data set that we will know is in the feature part, and the part of the data set that we don't know is the label, which is the in this case the number of items, the number of purchases. So first, what we need to do is to split our data into parts. The 80% will be for training and 20% will be for testing. We need to do this so we can train the model with as much data as we can, but we need to save some to evaluate that the model that we trained can perform predictions for unknown data, for data that the model hasn't seen before, with a certain level of accuracy. So that's why we save this 20%. So then we initialize a random forest regressor. We provide the label column and the features column, And then we can set up some parameters that this algorithm accepts, such as the maximum depth of the decision trees and the maximum number of trees. So you can actually play around with those, so you can get maybe better results than we did. Then we can train the model with the data that we have and predict it for the data from the test data that we saved in the beginning. And then we can evaluate how good our results are. And we will get a measure, RMSE, root mean squared error, to evaluate how good these results are. Obviously, closer to 0, the RMSE is, the better. So once we have our trained model and we reach a level of error that is acceptable, we can save this model, so we can later use it in another program to perform predictions. That is actually the next step in our process, which will be using dates that haven't occurred yet, dates from the future, and use the model that we just trained to predict the number of purchases. So since a prediction can, the supermarket manager can perform a prediction anytime he or she wants, we need to use Spark streaming to listen all these prediction requests, and so we can use the model to get a result in real time as soon as it's available. So if we take a look at the prediction job, we'll see it's fairly similar, but instead we use the Cosmos connector for Spark streaming to receive a prediction request right into our program. So every time we receive a new prediction request, we retrieve the different parts of the date that we want to perform the prediction for, and we use the model that we trained before, which we import here at the beginning. Here we import the model first, and then we can use it once we get a prediction request to perform the predictions. And once we have our prediction, we can write it in the context broker using the Orion sync that the Cosmos connector provides. So the other fiware components, which we will see now, so they can use the results to show it to the end user, in this case the supermarket manager, and maybe store the results so we can later check them out. Okay, so obviously we cannot expect a supermarket manager to use Spark, Scala, or any sort of any tools of that sort to perform predictions. We need to provide this person with a usable user interface, a graphical user interface, so he can make use of our application. So we have developed a web application in which the supermarket manager can select the date for which he wants to perform the prediction and get the result, the estimated number of purchases right there. So now our challenge is to use fiware to do the whole process of getting the date from this application, send it all the way to our Spark job that performs predictions, and get the result back and as soon as it's available to the supermarket manager through this application. So now Andrés will explain step by step what goes on in this architecture that we saw at the beginning to do exactly this. Andrés, do you want me to skip the slides for you, or do you want to present?
For me, it's okay that you.
Okay.
Okay, this is the whole picture of the scenario that we provide in the example. So in this case, we have the first interaction is when the user goes to the web application that is a Node.js application and make input some data for making for requesting a prediction. So this is the first step when the user goes to the application and then fill all the information, and this information is going to directly to the context broker. So as you can see, the information that we need to make the prediction goes to the context broker. So the four step indicates that the big data cluster has a subscription to the context broker to a specific entity. So in this case, all the information, all the request goes through the context broker to the big data cluster. In this case, it's a Spark master and a Spark slave using the fiware-cosmos connectors for connecting with the context broker and the big data cluster. Once the data goes into the Spark master and slave, we calculate the prediction using the previous jobs that Sonsoles presented before. So using the prediction job, we have the prediction, and this prediction is sent back to the context broker, as you can see in the step 5. All of this information goes back to the context broker, and then we have also subscribed Draco to the context broker for storing all the information in MongoDB. So we don't only save the last value, but also we save all the data that comes to the context broker. So all of this information is stored in MongoDB and also is sent directly to the web application. So we have a real-time prediction that is presented finally to the user. This is the whole scenario that we have. We want to provide you in the GitHub repository for that you want to, if you want to play with these things. Okay, another thing that is important to present is how is the entities and the subscriptions created in the context broker. As you can see in this slide, we have a graphical representation of the entities that we have in the context broker. From one side, we have the request ticket prediction entity that is directly related to the request that we made with the web application. This entity have a subscription that is a subscription coming from the big data cluster that is, in this case, is the Spark master. So every time that we make a request or the entity of request is change any attribute in this entity, this will notify to the Spark cluster. So with this information, we can perform after the prediction. We have also another entity that is the response entity of a prediction. So this entity has two subscriptions, one from the web application and one for Draco for storing the historic context. So in this case, when the Spark cluster make the prediction, it sends to this information, this prediction, to the response entity to the context broker. So as the attribute change, we receive the notifications to the web application and also in Draco. In the right part of this slide, you can see more or less the structure of every entity that I mentioned, so you can more or less scheme how it works. Finally, we want to provide you also a repository with all the scenario containerized in order that you can start to play with these things. So To set up this scenario is very easy. You only need to have a Docker Compose and clone the repository and do Docker Compose app, and then open the web application to interact directly with all the pieces that we have in that repository. So in order to show you a better representation of the whole scenario, I want to present you a little video that includes these interactions. Okay, in this case, the first things that you need to do is obviously clone the repository and then perform a Docker Compose app. Okay, as you can see, all the containers are creating, so I want to show you the structure of the Docker Compose. We have the MongoDB container, the Orion container. We have also the web container, that is the web application for interact the user with the prediction things. We have also in the web application the commands to create the entities in the context broker. We have also the Spark master and the Spark slave containers for performing the predictions with the whole running jobs. We have also a Maven container for creating the jar that after we upload to the Spark cluster. We have also the Draco container for storing the context information, and finally a Python container for performing some operations related to the automatic creation of the processors and configurations in Draco. This is a structure of the Docker Compose, and as you can see, once a whole is running, we have ready to make a prediction. So the first things that we need to do is check that everything is okay in Draco. As you can see, we have all the processors up and running, and then we can go to the web application in order to set all the parameters to perform the predictions. In this case, we use the web application, put one date at one time for make the predictions, and we can see the whole operations is going through the context broker, and then the big data cluster, and then the prediction that we make. And you can see in the slide, we have a prediction of purchases in this case. We can make any prediction that we want in different dates and different times. And this is a very good example because you can see we have a lot of purchases in other times, but when we set the time to the midnight, we have also a little quantity of purchases. And that seems that the program works well. We have also another thing that is we can show you the historic of the whole interaction that we made in the application, and this is also allowed and thanks to the use of Draco. This is a little check of the whole information that we receive in Draco, and we persist in this case for this scenario in MongoDB. I think this is a very good example that we want to show you, and it's easy to set up and for start to playing with the whole thing on machine learning with the with fiware components fully integrated using all of these generic enablers. So thank you for your attention. If you have any question, please let us know. We are here for answering everything that you want to ask.